Okay, welcome back. Now, last time we just introduced you to the Fischer projection formula, and I gave you certain rules for maintaining the integrity of the formula, that you cannot rotate or change the position of the groups or interchange the position of the substituents at your will. There are certain rules. One, I said that 90-degree rotation is not permissible, whether clockwise or anti-clockwise. Now, suppose I take a molecule like this, let us see which one fits to it. So, I have drawn the Fischer projection formula of this molecule. So, you see that I am holding it, that what it is supposed to be when I observe from here. These two are towards me and these two, the vertical bonds, are away from me, and then I draw the projection on the plane, on the reference plane. So, I have red on the green on the right, blue on the left, red on the top and white at the bottom. So, this is the molecule. Now, I am rotating the, see, if I rotate this molecule by 90 degrees, it does not matter, it remains the same, but because it is a 3-dimensional projection formula of this, I have to follow certain rules. I say 90-degree clockwise rotation or anti-clockwise rotation is not possible. So, what happens there if I do that? So, I just give an example that I do a 90-degree clockwise rotation. So, R comes here, green goes there, W comes there and B goes there. So, what is the relationship between these two? Now, I gave you one rule that exchange in a group of 3 is permissible. So, let us try to match these two by this exchange in a group of 3. So, how do I do? Because everyone has changed their position. So, I have to slowly bring them to their normal position, what is here. So, if I try to bring B here, then B will come here, but I have to do another exchange in a group of 3. So, W has to go there. So, W comes here, because the way I am doing it, so that two groups at least come in the respective positions if I do that, but then G has to come to the position of B. Okay, this is exchange in a group of 3, that is allowed. So, now what is happening? This is equivalent to, this is B, this is B, this is W, this is G and this is R. Okay. Now, what remains? The remains that the, now you cannot see, you have the W here, W there, you have B here. The only problem is you have G and R, they are interchanged with each other. And as I said, one, if you want to now interchange these two positions, that is not allowed. So, what I do again another exchange in a group of 3, and it will be interesting. If I do that, then B will be here, keep the W there, and R will be at the top and G will be at the bottom. Now, look at these two molecules. If I put it here, unfortunately, it is actually drawn in the down in the bottom, but if I place it on this side or if I place it on that side, maybe I can draw it again. The same thing I am drawing. So, B is here, G is there, R is here and W is here. So, what is the relationship between these two? Now, you see that they are enantiomers of each other. That means, if you do this 90-degree clockwise rotation of a molecule with a single asymmetric carbon or chiral center, that what happens? That you change the molecule into the enantiomer. Okay. So, likewise, you can, in this way you can prove the other restrictions or the allowable operations that are there in the Fischer projection formula. In the same way, like the other one, I can do the other one, that what I said, that 180-degree rotation is allowed. Okay. So, I again draw the same thing. This is now blue, this is white, this is green and this is your red. So, if I do 180 degree in plane rotation, So, G will be there and R will be here and B will be there and W will be here. Okay. That is 180 degree in plane rotation. Now, if we want to compare these two, what we need to do? We again want to try to bring the groups in the respective positions. Okay. So, R was down. So, what I will do? I will change R, bring R here and then I bring G there and I put B there. Okay. So, now sorry, what happens? R goes here, sorry, maybe it will be the other way around, because I want to put the G, okay, I want to put the R here. So, R there, G here and B there. So, if you do that, so what will happen? So, here it will be R, here it will be G and here it will be B and W remains at the same position. At least R has come to the place where it was originally. Now, I do another exchange in a group of 3. So, I bring G here, I bring B here and I bring W here. So, if you do that, you see that B is here, then W is here and G is here, R is there. Now, compare these two, they are same. R is here. So, they are the same molecule. That means, 180 degree in plane rotation is allowed. 180 degree out of plane rotation is not allowed, because what you do is you change the, because these two bonds are towards you. So, if you do a 180 degree out of plane rotation, you are disturbing the Fischer projection, the basic premise of the Fischer projection. These two bonds will become alpha and these two bonds were earlier alpha, that means the dotted ones away from the board, but if you rotate it by out of plane, so they will come towards you. So, you are violating the basic principle of Fischer projection. So, that is why any out of plane rotation is not allowed in Fischer projection. So, I can write it, any out of plane rotation is not allowed. And the simple reason is that you disturb the alpha beta above the plane or below the plane. I should have mentioned it earlier, when you darken the line, that is designated as beta, and when you dotted the line, that is designated as alpha. So, the alpha beta nature, like these two bonds should be beta in the Fischer projection, but as you lift it up and bring it out of the plane, the alpha beta nature gets disturbed. So, that you cannot do. That is why those rules were framed in Fischer projection. Another is question that may come in mind, because in several books it may be written that two exchanges are allowed in Fischer projection. Two exchanges are allowed. Now, this is true only for compound containing a single chiral center. This is only applicable for a compound containing a single chiral center. That means, if you again have, say, suppose the methyl, OH, chlorine, fluorine, if you do two exchanges, that means not in exchange in a group of 3. See, if I interchange the position of this and that, if I interchange the position of this and this, that is allowed. Okay. But I did not mention it as a general rule, because in general it is only restricted for a single chiral center containing molecule. When the chiral center increases, this rule will fall apart. I can give you an example. Suppose tartaric acid, if I write tartaric acid OH CO2H H, this is the Fischer projection formula of tartaric acid. Now, if I ask you to convert it into the wedge formula, you can, that means the wedge formula is carbon, this is the beta bond OH, this is the beta bond H, this is carbon, this is the beta bond OH, this is the beta bond H, this is COOH and this is COOH. This is the wedge formula. Okay. Now, as I said, if you do two exchanges now here in this molecule, suppose I change this one, the OH with CO2H, and I do change the, so OH comes here, COH comes there, H comes here, and I do another exchange where OH comes here, CO2H comes there, this molecule, this is not the right example. Maybe I can, I think I change this into little bit into another system, say fluorine. Okay. So, replace this hydrogen with a fluorine. So, the fluorine now stays there. So, it is not a tartaric acid, it is now a fluoroderivative of tartaric acid. I draw the Fischer projection, I do two exchanges, the OH and CO2H, and here the OH and CO2H. And what will happen, that you can try at home, that these two now becomes diastereomers. They are no longer the same molecule, although you have done two exchanges. The interesting point is these two exchanges you have done on two different carbon centers, two different chiral centers. Okay. So, the actual, if you want to stick to this two exchange rule, you have to say that two exchanges at a particular chiral center is allowed, but two exchanges at different chiral centers will lead to diastereomers. Okay. You can, through problem solving approach later on, we can clarify the doubts here. If somebody has any doubt, this can be clarified by working out several problems like this. Okay. So, this is all about Fischer projection. Now, there are other projections, as I said. The second one is what is called Newman projection. Newman projection formula. Now, in Newman projection, what you do, this is not for a single carbon containing compound. This Newman projection is usually two carbon containing compounds, that if you have two carbons joined to each other, and then in Fischer projection what you do, you hold it in such a way so that the horizontal bonds face to you, then you can draw the Fischer projection straight away. In Newman projection, rather than looking from this direction, what you do, you turn the molecule in this direction and then try to see from the carbon-carbon axis. So, if you see from the carbon-carbon axis, basically this carbon is not allowing to visualize the other carbon. So, that is blanked out by this front carbon. So, this is the front carbon, this is the back carbon, and this we in Newman projection, this is denoted as a dot for the front carbon and a circle for the back carbon. And in the front carbon, now you have, so the carbon-carbon axis is basically you cannot show, because this carbon-carbon axis, this carbon is blanking out the other carbon, it is exactly in the line of your vision. But what you have, that in the front carbon you have three bonds apart from the carbon-carbon axis, which cannot be shown, and in the back carbon you also have three bonds. So, now you take the projection of these bonds again against a reference plane. Suppose I have a reference plane here in the board, and I take the projection of all these bonds in the plane of the board. So, what will happen? The front carbon has 3 bonds. So, you can have 3 bonds like this, and if you look at this tetrahedral carbon, although the angle is 109 degree 28 minutes, but actually when you do a projection, it will look like that they are having 120 degrees. That is in the projection. Again I repeat, actual angle is 109 degree 28 minutes. So, now you can have 2 extreme cases. In one case, you can have the bonds, the other bonds, that means the other carbon, the back carbon also had 3 bonds, but because the back carbon is blanked, cannot be seen due to the front carbon, but what you can see is the bonds. So, the bonds to actually show that this is the back carbon. So, you aimed the back carbon at the circumference of the back circle. So, these bonds belong to the back carbon and these bonds belong to the front carbon. So, this is one extreme case where it looks like this, when it looks like this, and there are other cases, actually there are innumerable projection formula you can draw, that you can draw a projection which looks like this. Say some angle is made, that is also possible, but that is also a Newman projection formula. The basic premise is that you hold it, you should see the molecule along the carbon carbon axis and then draw the projection, and the way to represent it is that the front carbon is shown as the dot with 3 bonds, and the back carbon is shown by the circle, and the bonds ends at the circumference of the circle, but actually they are joined, they also go up to that carbon which is not seen, because we are seeing from the front. Okay. Now, there are extreme cases, like in this case, what is the dihedral angle between these? This is 60 degrees. The dihedral angle between the plane containing these bonds is 60 degree, and there is another extreme conformation. These are called conformation. I will come back to that conformation. What are the conformations? Conformations are this: by rotation you are actually changing the dihedral angle between the several carbon containing groups. I am just drawing 2 extreme cases. The other one is that you can have another form which will look like this. This is called the eclipse form. You have to slightly shift it, because otherwise actually this is perfectly, this is actually blanked out by the front substituent, but in order to show it in the 2 dimension, we just shift the bond a little, so that these are visible. Okay. So, this is what is Newman projection. Now, this type of conformation, again I repeat, conformation is basically the innumerable forms that you get by rotation around carbon carbon single bonds. Okay. So, here we have drawn only 2 extreme conformations. We will come back to conformation concept later on. This is what is called a staggered conformation, and this is the eclipsed form. These 2. Okay. Now, there is a third one which is called Sawhorse. Sawhorse projection formula. So, what you do here, the carbon carbon bond is drawn in an angular version. Here, where is the carbon carbon bond? The carbon carbon bond is actually not seen, because it is actually along the line of axis of viewing the system. In Fischer projection, the carbon carbon bond is visible, because you are seeing it not along the carbon carbon axis. So, that is why this carbon carbon bond is visible in Fischer projection. in Sawhorse formula, you put it at an angle and then draw the other 3 bonds attached to it. So, this is the carbon carbon bond and the other 3 bonds will look like this. So, this is the Sawhorse representation, where of a here this bond is eclipsing this one. So, that is the eclipsed form in Sawhorse. And what is the other form? That means the staggered form. You rotate one of these by 90 degrees, keep the top one maybe in the same position and the bottom one you rotate. So, you get, if you rotate, that goes to the top, this comes here and that goes there. So, this is what is the staggered form. Okay. So, basically what we have done till now in these past few lectures, that first of all how to represent the 3-dimensional molecule into the 2 dimension. But the first we started with that how to use the wedge formula. The wedge formula actually is a 3-dimensional, correct 3-dimensional representation, where the bonds are appropriately shown, that whether they are above the plane or below the plane, that is called the wedge formula. But wedge formulas are little difficult to handle, that is why that gave rise to this concept of converting them into 2-dimensional projection formulas. The first was Fischer projection, which looks like this for a 2 chiral center containing compound. Then we have the Newman projection, where it is viewed along the carbon carbon axis, and the third one you have Sawhorse, where the carbon carbon bond is aligned, is drawn in an angular fashion, and the other 3 bonds are then projected along the plane. Okay. And you can have, see, the problem can be given that how to convert a Fischer projection into a Newman projection or a Sawhorse or vice versa, the interconversion of all these things. Now, one thing I should also write here, that what is the wedge formula. If you convert it into the wedge formula, how will it look like? If you convert it into the wedge formula, then it will be that this bond is in the plane of the board, and this bond is also in the plane of the board, and this will be beta and this bond will be alpha, and this bond will be beta and this bond will be alpha. This is the wedge formula, wedge conversion of this Sawhorse formula, Sawhorse projection into the wedge. So, likewise you can actually, I can give you this problem, that I give you the wedge formula and then convert it into the Fischer projection or in the Newman projection. So, lot of problems can be generated by through this interconversion. Okay. So, this is a very important concept. You have to learn how to draw the correct Fischer projection formula of the Fischer or Newman or Sawhorse, whichever you are comfortable with, and how to draw it correctly and how to interconvert them correctly. Okay. So, that is the different 2-dimensional representations of the 3-dimensional molecule, because remember the chiral molecules are all non-planar molecules, they are not planar molecules. Planar molecules cannot be chiral, because all planar molecules have a plane of symmetry. Planar means it has got plane of symmetry. The plane itself is the plane of symmetry. So, what we are dealing with, all the chirality means 3-dimensional geometry. So, this is very important, that projection formula, use of projection formula in describing the stereochemistry of the molecules. Okay.